So before proceeding with our convolution algorithms on Nexys A7, I would like you to know more about the company in which I'm working. We are Digital Technologies. We are an industrial and academic partners in test and measurements. We work on automation sectors, FPGA development, wireless technologies, AI-driven IoT solutions, and training and skill development and e-learnings. So we have provided n numbers of solutions to a variety of customers. We have even worked on different sectors, and academics is our major area of focus. So I am Ashutosh Tiwari. I'm an FPGA design engineer for 2.5 years of experience. I've worked on various domains for image processing, audio processing, DSPs, and wavelength cameras. Along with that, we also work on the USRPs, high-end USRPs for 6G, 7G, up to 170 to 180 gigahertz. Ask. So I have worked on a variety of boards, which are Vertix Ultrascale, Vertix Pool, Vertix 7, Altera boards, and Zing 7000. We have lots of high-end FPGAs are developed from our end. So we are completely a research and development industry, which we have completed 7 to 8 years of experience in our end. So before proceeding with what is the digital image processing part, so I would like to know where are the actual applications where FPGAs are used and the actual applications which are developed by high-end industries. What is the role of FPGA and where are image processing practically used? So image is a visual data, it's an intensity value what our camera captures and it tries to display at a certain resolution format. So it is used on lots of applications like surveillance, medical, MRIs, and robotic applications. Smart AI integrations can be implemented through that visual data. So basically, people try to implement it on GPU, graphical processing unit, microprocessors, FPGAs, Arduinos, Raspberry Pis, to manipulate those digital data and to extract that useful information to our end. So the today's development, the upgraded technology basically implements artificial intelligence on MRI, CT scannings. So it is a high intensity of threshold which are manipulated, and based on that intentional threshold value, we try to present our image in a certain format, which is used in our medical applications. Remote sensing is wireless communications, which we try to receive through integrated and high-speed antenna, and we try to get a satellite imaging for very high distance planets. Industrial applications is for monitoring high-end machines, automation machines, and huge lorries, PCBs are included for high-end data manipulations and algorithms. Securities and surveillance is a very crucial aspect on defense industry because our defense areas, lots of trespasses can be identified through our artificial intelligence. We can also integrate lots of wavelength cameras, high intensity wavelength cameras, medium wavelength cameras, short wavelength cameras, and long wavelength cameras for securities. Surveillance, we can include facial recognition, object detections, are the few artificial intelligence which are suggested by our defense sector. Automotive industry, what we see at today's end, lots of electrical vehicles and EV vehicles, whatever we see at today's upgraded technologies are only meant from FPGA part. Our FPGAs, basically NIS videos, are used for EV vehicle charging, EV dischargings, and car automations are used as an automotive industry for us. Entertainment and multimedia is what we do at today's generation for transmitting and receiving video transmissions at very high distance. And multimedia communications like wireless communication like Bluetooth, and 5G to 6G network entertainment are completed by our FPGA domain. Document processing is an handwriting recognition, what it's used. So we can implement an artificial intelligence on that documental process to understand the actual coding. So why are we choosing FPGA in all this? So FPGA is a core domain because it is used for very high latency, our synchronization period, and it is done at parallel computing process. So with parallel computing, we can process a lot of applications at one end. We also have a privilege of designing your own design or neural networks or any image coding processing codes, audio processing codes. All those codes can be completed through our high-end FPGAs. So that's why we are choosing FPGA for image processing or wavelength cameras for this particular reason. So once we finish with this, let me show you that why are we using Nexys A7 camera for this. So this is the top level architecture. What we are seeing is the top level architecture of our OV7670 camera, and this is the OV7670 capture module. So this is how the camera, a CMOS camera, what we see, the CMOS cameras is giving a very fixed 8-bit data, pixel values at 2 bytes. We receive that in a perspective of pixel clock, and based on the vertical synchronization and horizontal synchronization, we try to capture this module and pass it to a simple storage, dual storage RAM. And based on that, we give an output of this frame address and frame pixels. So this is how the top level architecture of our coding design for our today's webinar is. OV7670 camera is a CMOS sensor, what we use, and it is capturing a pixel bit data from its end. And based on the capturing part and the interface, it is doing an I2C protocol to give a register mapping to this OV7670 camera. So this register mappings is deciding what bit of resolutions we are trying to out to this camera module. Once that pixel clock and pixel bytes is received from this captured module, we are trying to synchronize this in a format where you have to store all those pixel informations in a simple dual port RAM. So the reading part and the writing part on which you are writing this memory at 12-bit rate, and you are outing this 12-bit output to a VGA monitor, an IC code, which is practically giving you those pixel data on certain conditions and frequencies. So this is the write address which we use to write in our VRAM. And based on my write address, my VGA is going to read that many addresses from that OV7670 using this memory VRAM interface. VGA top is a output model. It is an IC which is present on Nexys A7. OV7670 is a camera model which we have taken through a general purpose input output. So based on GPIOs, we are receiving this pixel informations, we are capturing it out, we are converting this into 12 bits, and the camera capture is completed only by this I2C settings. So the X clock, what you see is the master clock, which we have to generate through our RTL code. So once the data is completed, the data is captured and passed through this VRAM. We write those pixel data after completely capturing the whole pixel per frame. And after writing, we read it out through this VGA monitor and we send it as an output from our monitor. So why should you try to take a CMOS camera, OV7670 camera? What is the reason you are choosing this? Is because it has a lot of functionalities which can be implemented through digital and analog part. So first important thing what we can see is that it contains that array control and frame generation part. So based on those pixel arrays, whatever we try to receive, it has been received from this array and the frame is generated digitally from this output. So the CMOS camera is practically taking our optical sensing materials, it is sensing that and it is converting into digital signals and sending it out through that part. So internal timing signal generation is completed by this OV7670 camera. Based on this, our I2C settings for SC and SCL, it is going to give you the output completely based on your internal timing output. The frame rate has a refresh rate of 30 Hertz. We have even implemented 60 Hertz on this timing part. So what is the another important factor what you have to see is that in OV7670, you have to see that the automatic exposure control is completely controlled by our I2C settings. So based on your automatic exposure control, the I2C settings, what you do on that part, you are converting this exposure part. You have the independency of changing that exposure. So analog part, like I said, that you are using the optical sensing material is sensing the light materials and it is generating a digital signal based on this. So automatic gain control and automatic white balance are the two factors which are computed by the analog part of this. So this is the CMOS sensor which we are receiving. This is the actual output format what you are seeing from this our end. So the camera is controlling the standard serial control bus through SSCP protocol. SCCB is the serial camera control bus which you have to configure in your I2C to operate it up to 30 frames per second to output you the resolution of 640 to 480p resolution. So your VGA is generating this figure 3, what you see, the optical sensing materials is practically burning. For every input materials, whatever you see, you have to burn the CMOS every time at once. So the CMOS sensing material, once it burns, it is generating you the 3 components, the blue component, the green component, and the red component. So once this camera module has completely captured, if it is generating all those red, green, and blue components, so you are converting and you are writing a timing diagram in your RTL where you are latching this red, green, and blue component on a particular conditions. So you may see that this BP, display, and FP, this is the back push, this is the displaying part, and this is the front push of your displaying sensor. So like I said, that once the OV7670 camera is burning, the CMOS sensor is burning, and it is generating those pixel values for red, green, and blue component, my camera has to capture it at 24 megahertz of clock. Once my 24 megahertz clock, the camera is captured and all my data are latched at this point, I have to send those data output as output to that VRAM, and it has to be read through the VGA top model. So this red, green, and blue component, what we see is this is how we have to latch those red, green, and blue component to complete that pixel values. So for every vertical synchronization, it will have all the horizontal synchronization will be present on the whole vertical synchronization part. So the back push, the displaying part, and the front push has to be done at a certain pulse width. So for every one vertical V-sync, all head-sinks will be present in that part. So when the displaying part is present, the red, green, and blue component can be latched on that timing diagram. So like I said, to find that VGA image array, you have to, the pixels are sent as 2 bytes of packets. All those pixels, what you see, are sent through this camera sensor in 2 bytes. The 2 bytes, whatever we send, are latched and received at this in a 12-bit format. So this is the functional block design for my OV7670 camera. So this is the SSCB interface, what I have told as serial camera control bus. So based on this serial camera control bus, we have to configure your I2C settings. Based on your I2C settings for your clock and data, the register mappings are stored on this register array. So once the registering part is completed for your registering part, you have to go for automatic exposure control. This is the automatic exposure control, and this is the automatic exposure gain detection. So once that gain and exposures are completed, it generates a digital video timing. Complete video timing signals are generated from this output part. The data pins are shown in that. So this red, green, and blue component, what you see, this is something which is coming as an analog to us, and these analog values are converted into digital output format. So once it is converted to digital output format, it is going to the DSP engine. The DSP engine and image scaler are removing the noise patterns, what we are sensing from our output format. So after sensing the output, we are sending it as a video port, and we are practically sending the output from that part. This is the RTL coding, where the register mappings which we have done here. Those register mappings are going inside my configurable center part. The I2C sender is practically taking my register mappings. It is taking on certain commands. It is sending you the serial data and serial clock. These two outputs, what we see is an input to this serial camera control bus interface. The X clock, what we see is the master clock, which we are taking as the clock divider based on this output format. So you may see the timing diagram of my I2C settings is the SOIC and SIOD, the serial clock and serial data. For every clock, we have to first latch my EEPROM slave address. The slave address for my I2C setting is 42. The address mapping for which address you want to write, that we have to latch it on the second part, and the third part will contain the value, what output value you are expecting from that I2C registers. So this is how the pixel clock, the RGB565 output format is completed from our end. So the pixel clock, what we see for pixel clock, this has been generated as an input to our RTL. For our pixel clock for I2C settings, what we said, it generates an clock for us. So based on this clock, we try to take the reference, the H sync and the H reference is completed from our. So the row pixels, what you see, this is practically the pixel address, what we are trying to configure on that. So data output 8-bit latch, what we see, these first bit and last bit are generating for my output format. So the first byte, what we see, like I showed in this output format, that where pixels are sent as 2-byte packets. These 2-byte packets, the first byte is considered based on only red component and green component. Only first byte will contain the red component and green component, and my second byte will contain my green component and my blue component based on this array vector. So first byte is latched, or it is received when you are receiving on the negative edge, the T pixel clock. Whenever you receive the edging part, you try to latch and take out the first byte of your data. So once the first byte is received, all that red component and green component comes on the first array. The second byte will contain the green and the blue component. So this is how that row 0 to row 1 till row 480 we try to analyze and we try to send it out. So for every timing display, this timing display, timing PW and timing front post and displaying part, for every line address of 521, only 480 lines are visible for you. So like you may see in the timing diagram, for 510 into T line, only 480 into T line is the visible part which you can see in your output format. So the clocking part, the number of pixel address, what you see is 640. So 640 is basically the active resolution part of our output format. So if you see this part accurately, you may see that this is the one vertical synchronization. In one vertical synchronization, there is a front post, back post, and the display type. So the 640 is the actual displaying format of 640. Only 640 is the displaying period. Only in this period, we can latch our red, green, and blue component. My back post or front post are invalid. You may see that no data we are passing no data on this timing output diagram. The timing is only displayed on 640 and 480 resolution output. So this is how we are completing 0 to 639 addresses. So the 0 pixel address to 639 is the number of rows what we try to see. For every row, for 0th row to last 479th row, all my headsink, all my data will be connected for my first pixel address. So based on that, it is continuously going till 480 lines. So 0 to 479 is my line address. So the actual display time for generating 640 to 480 resolution, you have to count for a period of 800 and 521 lines has to be counted to generate that output. This is the actual flow diagram. Before we proceed with that, let me show you the actual coding format which I was telling in a visual manner. Here is where my first pixel address is starting from 0 to 639. For every 0 to 639, you have to count in 800 lines. 800 pixels you have to count, in which only 0 to 639 is your actual horizontal display time. So this is the format where you are trying to present your horizontal displaying time for 0 to pixel 639. So it goes again as it is refreshing completely. It is going to the second pixel, third pixel, and fourth pixel, the first line, second line, and third line, fourth line, till it reaches this 479th one. So to reach from 0 to 479, it has to count a total vertical period is also required for this. So the front push and back push and the horizontal sync signal is required to complete the whole frame data values. So this is the red component which we try to send as an output to our VGA output format, my green component of 4-bit and my blue component of 4-bit. So based on those sync signals what we receive, we try to give the output of this. So pixel clock is my 25 megahertz, I'm sorry. So based on my 25 megahertz, I'm counting my horizontal count from 0 to 639. Once my 0 to 639 is completed, one horizontal synchronization is complete. So I will generate a horizontal synchronization. This would be my horizontal sync in this part. Next, after my one horizontal synchronization is completed, my vertical counter is enabled. So I have completed my first line address. Now I have to jump to the second line address. For my second line address, I have to count till my one vertical synchronization is completed. So for every pixel, for what you see from 0 to 479, this 0 to 479 is the total resolution. So that much line it has to count to generate one vertical synchronization. So this is how we set the horizontal synchronization, and this is how we set the vertical synchronization display timing format. So this is the output of the IC what we use in our Nexys A7 with integration to CMOS camera. So what is convolution algorithm in this is the pixel what we receive from our CMOS camera. The CMOS camera is burning completely. Once the CMOS camera is burned and it is capturing all those data, those pixel data are stored in a matrix format. And once those affected pixels are there, we are involving a convolution matrix. A convolution matrix is what we have taken. So based on those convolution matrix, we are generating another output. So convolution algorithm is practically implementing a kernel to the image to extract the meaningful features and image enhancement process. So the image data and hardware optimizations are completed for this. So as I said that we are generating 640 into 480 resolution. So the VRAM depth what comes into the picture is what is the storage element? How are you writing it from your pixel address and how are you reading it out? So this is the 24 megahertz of clock what we are receiving, where we are trying to write our data from this, and 24 megahertz is the writing period and reading period is the 25 megahertz what we receive from this. So this VRAM has a FIFO depth of 307,200. I'm sorry, 307,200 is the pixel depth because we are practically storing these many pixel values, intensity values inside a storage element. So 640 to 480 is 307,200. So that is the depth we are trying to include in this one. So the storage element for the write depth we are using the convolution matrix. After completing all those pixel values, we are involving a kernel in this, and we can produce a lot of applications like Sobel edge detection, Gaussian filter. All those things can be implemented on our image processing using OV7670 camera. So what is edge detection? That is a very important application in today's visual processing unit, is that the edge applications hardware, what we implement on real time, is a very important factor, because surveillance part, whenever we try to receive a horizontal, we try to detect many targets, we need a Sobel edge detection for that to identify those high intensity values. So edge detection is a technique used to identify the regions in which brightness of the images change sharply. So edges is a process where you are using Sobel filter and Gaussian filter. You can use Gaussian blur also, but canny edge detection, for every edges, like you said, it has to go through an image histogram equalization to equalize all those values to a particular intensity, and after generating a particular intensity for this, you have to apply a first order derivative for that. So canny edge detection, what we see is merging the weak edges and the strong edges. Based on that, you are generally passing 0 or 1 value to this. So 0 or 1 is how you will understand. The white and black value is what we try to understand, that is how many edges we are intensity values are present in this output format. So this is what demo. I will show the demo soon after, but this is how we are trying to generate a Sobel edge detection. For every high intensity values, the edges are considered as ones whenever the edges are present, and for rest of the values we are presenting as zeros. So these are the parts where it is changing. The images brightness is changing very rapidly. So you may see the timing diagram. Let me show you after my demo sessions. But this is the actual. If you try to see this, this is how it Sobel edge detections are used on various surveillance fields and industrial inspections and automation industries to understand the Sobel and Gaussian edge filter. So artificial intelligence is a very important process in FPGA. Why do you need artificial intelligence in FPGA? You can use it on embedded processors, GPUs, in a lot of things. So artificial intelligence is a very important part in FPGA, because today's technologies are only working. The wireless communication is working on artificial intelligence and visual processing. So this is the just so for the timing diagram, like I was explaining, the Sobel edge detection, this is how the artificial intelligence are actually implemented in our FPGA domain. The 28 cross 28 pixels is what we are taking as the resized output format, and we are passing it to a convolution neural net. So our OV7670 camera can present this output format, and based on this, it can show you the output screening structures for us. So we have implemented an OV7670 camera artificial intelligence for numeric number detections. So number detection is what our priority was for detecting the applications for OV7670 camera. So the optimized architecture where the computing frequencies are less than 27 microseconds, that's how fast the predicted layer is going to detect and pass that input values to this convolution neural network. So the classification is more than 80%. So accuracy of our camera in CNN architecture is more than 80%, and it can find the digits of 0 to 9 can be computed, and the frame will freeze and show you the output of this output convolution format. This is the Nexys A7 hardware which we are using, the intelligence format. And these are the tools which you can use if you try to understand more about that Nexys A7 format. We can use Vivado, we can use LabVIEW, we can use Xilinx Vitis to create your own custom IPs. We can use OpenCV platforms, Vitis and Multisim for digital circuit designs. MATLABs can be used for wireless communications, for on-frequency density modulations, and quadrature amplitude modulation. Those things can be implemented through this MATLAB to explore the wireless part of this. Vivado is basically used for block design, and lots of processor block designs can be used on this Vivado output. LabVIEW is used for NI USRPs. We try to do the USRP programming through LabVIEWs. Xilinx Vitis HLS is used to create our own custom IPs based on custom IPs and OpenCV platforms. We can try to use the Vitis IPs along with this. So Vigilant NI FPGA hardwares, we have lots of FPGAs on that domain. We have Genesis Zinc Ultrascale, we have Genesis 2, we have Pink board, we have Z board, Zybo Z7, Nexys A7, Basis 3 board, and USRP B2 series. Lots of Vigilant NI hardware solutions can be presented to us. So we can show you a lots of AI powered solutions in our FPGA on real time. But before proceeding with that, let me show you the demo for this output. Can you play your cartoon? The cartoon take. No, not seeing this one. So my screen is visible for everyone.
Yes, it is visible.
So this is the increase and decrease brightness, what you see in this code. You may see OV7670 camera is my CMOS sensor, which is trying to give you the output for this. So yes, can you stand for this? Yes. So this is the increased brightness where we have done it through RTL part. So based on this increased brightness, my CMOS OV7670 camera is capturing burning continuously using the I2C protocol. This is the general purpose input output which we have used to give it this camera as an input interface to this. The pixel data, whatever you receive from this end, are storing on a local VRAM given by this Nexys A7. This VRAM is storing 307,200 pixels of intensity informations continuously and writing it from this part. We are reading those pixel data, converting it to 12-bit and passing it to this OV7670 camera form. So like I told you, Sobel edge detection, this is a very important convolution algorithm which is used by many customers, many of our research development part, how to implement Sobel filter, Gaussian filter, and other parts. We even have image sharpening, how you can do the image sharpening on this part. We have RGB to gray conversions. This is the edge detection using Gaussian filter. The Gaussian filter is used to detect the edges points. The motion blurring, the green filter, the red filter. This is how you decrease the brightness. So RGB to gray conversions, all those output formats there. So does anyone have any doubt in this demo before we proceed with the RTL side?
Please raise the hand if you have any doubts.
So does anyone have any doubt on this demo? Okay, someone has raised their hands.
So I have a one query.
Yes,
Yeah.
Sujit, you can talk now.
So can we perform this activity using NI CDO 9048 FPGA, or is it possible?
They bring charger. Charger. Yeah, so can you just tell me what doubt you have?
Yes, sir. Actually, my query is
Sorry, I'm not able to hear you. Really sorry.
can we use NI CDO 9040 FPGA to perform this activity? Is it possible?
Just give me 1 minute. See, I'm not using audio only. What should I say? No one is speaking. She's speaking. No one is speaking. No one. How can I put a message? Put inside box. There.
Yes, Ashutosh, your screen is visible.
Yeah, Subodh Singh, can you just ask me? Like, I'm not. I think your audio is not audible. I guess I'm not audible.
Yeah.
Can you just put your message on the chat box so I can see?
Yes, yes.
I think your mic is mute. That's why. Yeah.
Yes, I have put the query in the chat box.
Okay, so you are using NI serial N04945 FPGA to interface the CMOS camera. Yes, we can use it. We have certain P modes and general purpose input outputs are present for us. We can procure a vigilant P mode can be used along with OV7670 camera for this. You may see this output what I'm showing you here. Right? Can you just play that? Yeah. So the So like I said, it has a lot of video pipelines are present for you. So you may see this output, what we see in this part. It has a lot of filters, right? So my suggestion is that once you try to implement any GPIO cameras, if your device has a capacity to store at least minimum of FIFO depth of 3,07,200, it can easily be integrated in your RTX board. This is an RTX board you are using for serials. Yeah, we can implement on that. No issue on that. So this is, you see, this is how clean your monitor is. You are seeing the resolution output for this, right? So yes, we can include two serials 9045. We will see and will see answers. Any other doubt you have, sir? Okay, I have another hand is for non and ready, sir. Yeah, sir. Can you just say what is the question? Yeah. So actually, it is very pretty easy if your device has a capacity to store, and it all depends on the I2C settings, how the register mapping is completed for this part. So if your I2C register settings are completely good, then your output resolution format can be changed from 0640 to 485. Just yeah. So yeah. Yes, yes, I will show you the code right now. This is a complete RTL code. I have not included any block designs in this. And I have implemented all those algorithms on RTL format from RGB to gray based on my switch input model. You can see that based on my switch input model, all my implementations are getting happened. So the switch input, what you see in this uh, is written on this. This is the switch input for my increased brightness. If I remove this, I'll get RGB to gray form. Every output, the sawable edge detection, what we see, this is also done on RTL. No, we have not used HLS. We can use HLS for this, but like I said, we prefer the HDL part more. HLS is something we try to use it for convolution neural network. We can use HLS for something like this. If you want to implement artificial intelligence on your output format, you can use HLS on processes like this. So to implement DNN, deep neural network, artificial neural network, and artificial intelligence, we can use this. We have used it, but we have also implemented this convolution neural network in our Nexys A7 using camera only through RTL. We have not used HLS for this. We can use HLS for lots of domains, but these are the things we prefer RTL as our part. Is there any other questions we have? Okay. See, what is the harm if you keep your phone here for 4 minutes? I am not seeing the question. Okay. No, I'm not use HLS. So can I use camera like USB camera with this development board? Yeah, you can use USB camera for this. We have a USB port for this part. In order for us to work on this, do we have to purchase license from your free license? Yeah, it is a free license. The license is free for this free license. For this part number, this is an Nexys A7 part. You can use, yes, USB camera can be used for this output format. HLS part, no, we have not used HLS. We have written only on HDL and VHDL, VHDL or HDL format. Easier.
Anandi, you can unmute and talk to yourself.
Any other questions I can clarify before proceeding with demo part? Does anyone have any doubt? So for the output detection part, like I showed, this output detection, what is happening, this soluble edge detection, Gaussian, the sharpening filter, my output is reduced. We have included lots of image applications, but we have included our major concern is the good brightness quality what we receive from this one. So yes, let me proceed with the Vivado coding so you can understand this better. This is the actual code for my Vivado format. This is the switch input which I'm giving, a 4-bit switch input. Based on my switch input, my buttons are getting pressed, and my horizontal synchronization, vertical synchronization, and all my red, green, and blue components are going inside. So this is the pixel clock which is getting as an input to my OV7670 camera model. This is the master clock which I am generating from my clock model part. This is the vertical synchronization which it's going to take, my horizontal synchronization, and my 8-bit of data input. SOIC and SOID is my I2C register settings, and these are the another formats, physical pins, which we are passing it on our I2C values. So before proceeding with course, if any other questions anyone has, they can ask. Yes. The software using for this can use Python as well. Yes, you can use Python. Yes, but it will be only integrated to HLS. Why is HLS? So yes, you can use. Like I said, we have only used programming languages like VHDL, HDL. That is the only coding form which we have used till now. YT's HLS and Pythons are used for training cameras to use the implementation of artificial intelligence. So artificial intelligence would be something like this. To integrate the camera to this certain output format, you have to train your OV7670 camera to detect this number, what it's seeing from outside, and give you the output of 2. So this cannot be done through VHDL or HDL part. It can only be done through our Python for Python, MATLAB, or we have another TensorFlow. Yes, these are the softwares which we use to train those data. Your camera will take all those data sets, the weighted values for these data sets, and based on these weighted values, it is going to predict you the output in the final output format. So it is going to take the weighted formats and the bias, what we receive from this, and based on this weight and bias, it is going to activate the ReLU and sigmoid functions. This is something we will discuss on by our upcoming webinars. So I can explain you better how CNN actually works on our Nexys A7 board. So we have implemented it on RTX 10. So for that, the range or the parameters would be something like this. The resolution output format will detect from 0 to 9 for this data values, and the accuracy for this would be 80%. So to involve something like this, you can't use Vivado, Verilog, or YTS. You have to involve something called as YTS HLS for this. So once you get that part completed, it is going to activate your output, the weighted values in computing time. It is going to activate and predict those output values in your OV7670 is going to predict this value. And your VJ is going to output this, and your frame will be freezed when it is showing you this output. Anything else related to this convolution neural network? Any questions? Yeah. You have to use a certain Python functions. So like I told, RTL YTS HLS is going to give you OpenCV2 libraries are included in that. It is not something that is controlled by Vivado. It is something which is generated. Those custom IPs are generated from YTS HLS. Those YTS HLS IPs you are importing in your RTL design. So once you are importing in your RTL design, what you are doing is you are using OpenCV2 libraries. And based on those OpenCV2 libraries, you have taken those trained data values. You are just integrating that IP to your output format to integrate that visual processing unit. So White's HLS is used to generate no strong actually is, but let me give you a clear idea before you proceed with that. White's HLS is something that can be imported, that repositories are included in Vibod. Let me be more precise for that. So, like I said, the train networks, what I have seen, or what you can implement, the created IPs, there is no other way than traditional HDL languages. Yes, you can create your IP using C++ language. I am correct on that part. So once you create those YTC C languages, those YT's HLS is converting your C language to an RTL for you. You don't have to convert it. It is going to generate based on your bit stream that YT's HLS will generate your C language and convert into RTL generated netlist. That netlist is called in your actual processing tool. So yes, YT's HLS is used to is used to generate will generate your C language, C++ code to HTML automatically inside the IP. Yes. So yeah, I hope that is clearing your question. We can discuss a lot about YT's HLS. We use more of the YT's HLS part in ping board, like you said. But ping board is again YT's HLS complete integration is completed on that, and you can include a lot of Jing processors are used for this YT's HLS integration. RTX 7 we have used for only RTL design. So yes, we are more focused on RTL. YT's HLS we use only for convolution neural network. So any other doubt on convolution neural network? No other doubt we have? Okay, let's proceed with the coding part then. And yes. For any doubt, you can just ask me anytime. So Yes, this is how you can use convolution algorithms can be implemented. You may see that I am taking a clock wizard in this output format and I'm generating two clocks, a VGA output clock and my camera clock. These are the two clocks which I'm using in my using my clock wizard. Based on my clock input, I'm generating two clocks. One is 24 megahertz and one is 25 megahertz. So yes, this is the clock wizard terminal which we see. The clock terminal is taking 100 megahertz as the primary input. Once we get that primary input, we are generating two clocks which called as 24 megahertz and 25 megahertz from this output clock frequencies. So it in clock wizards it has a lot of ports, but the main thing which requires is the voltage controlled oscillator. The voltage controlled oscillator is required for this phase shift. It is a single-ended clock source input, so you have to enable your input buffer to your primary clock input. So this is the primary clock input which we are passing to this. And based on the primary clock input, we are generating an output of 24 and 25 megahertz. Those 25 megahertz, what we see is used to write it on our VGA output coding format. So you may see that the frame addresses, the frame write and frame read is all getting stored on this local VRAM buffer. So local VRAM buffer, I'm using a simple dual port RAM. Here I'm passing integer width, depth are completely integrated on that, and I'm passing the output. So this is the dual port RAM which I am using to write and read my VRAM addresses for this. Any other questions? I don't have. Now, the frame address is what I am writing from my VRAM and what I'm reading it from VRAMs are included in my camera capture module. The camera controller, this is the I2C settings which I am using to generate my I2C values. This is the practical I2C address for every address and every data. I'm passing the fixed predefined register values. These register values are determining the output resolution of your OV7670 camera. So this is how my register is getting register settings are happening on my OV7670 camera, and the FSMs are working on certain output frequencies. Yes. So I2C setting controller is completed on that. Now the VGA output is how I'm determining the resolution for my VGA count. So as you can see, my vertical counting and horizontal counting is completed. Only then my active area is enabled. And so when my active area is enabled, I'm sending my video on this output format. So blanking is my video part, which I'm passing through this. And my horizontal front post and back post, all those things are given as a constant parameters to my OV7670 camera. Now the filtering part, once the frame buffer, once it is trying to receive it out from this end of our address generation, I'm sending it on the filtering module code. So filtering module is where I'm receiving all my red, green, and blue components from this. And based on this red, green, and blue component, I'm manipulating all those pixel data manually in my RTL code without using any whitelist HLS IPs. This is the code for RGB to grayscale. This is how I'm going to increase my brightness. This is how the RTL for decreasing the brightness, color inversion, red filter, green filter, blue filter. The original image can be seen through this. The saw blast detection, like I said, is a very important. So it is using a pixel output, and based on this pixel output, you are getting the saw blast detected high intensity values. The edge detection RTL is on this. So does anyone have any question? Do they want to know the particular algorithm or logic behind this?
I request attendees, if you have any question or anything, any query, please raise the hand.
So once my convolution operations are completed, my RGB values are passed as the 8-bit components, and again it is going bypassed as the top module. The top module, the red, green, and blue component, what we see here, are directly assigned to the output format for this. So red, green, and blue is given as 4-bit per color component. This is the output for this. So the symbology, what you see in this, so every symbology has changed values for the toggle edge detection. For every edge detection, it is going to show you the character display for this OV7670. It is displaying the, for every switch input, it is going to display you the coding output format. So yes. So the symbology data are also passed in my RTL. So this is how I'm passing the symbology data values. Yes. The active part, I'm based on certain vertical countings and horizontal counting, I'm passing my string values completely on my output format. So the address generation, once it's completed, the output we pass it on red, green, and blue. So draw character symbology is something which we have used to generate a symbology for our own output format. Sorry, output formats, we will only see the output in this particular rectangular format part. So this is how we are changing the symbology for switching. Any other questions? So the character room and character distance, what we see, the filter, RGB, gray, all those are working on the switch input for this. Based on my switch input, I'm going to display the output of RGB to gray, gray detection. All those implemented are happening inside my RTL coding format. So this is the coding from CMOS camera to output VGA display. So based on display, you can involve any kernel according to your choice, independency. That kernel will give you an affected pixels, and based on pixels, you will give an output of that affected pixels as a meaningful data. Those meaningful data are also can be written on RTL side. You can use YTS HLS, OpenCV2 libraries can be used, MATLAB can be used, and LabVIEW is also used on this image processing domain part. This is something we have implemented on Nexys A7 for convolution neural network. So based on convolution neural network, we will show you the computing time frequency for how fast the computing frequency of our RTX board is. These are the tools which we use. These are the tools which we use for our YTS integration. Like I said, HLS along with this OpenCV2 and NI multi-stream LabVIEW. And yes. So I think we have to conclude this session. So for any questions you have, you can reach out to my mail ID. My mail ID is ashutosh@digitooltech.com. You can contact me Digitool, and you can solve any queries. We can do integrations on lots of FPGAs. We worked on a lot of FPGA wireless communications for those 2 months, and we'll complete the sessions.
Uh, hello, all the attendees. Like we just have 2 minutes. If you have any doubts, any queries, please raise the hand. Thank you, Ashutosh. Thank you, all the attendees, for joining in.